right, so in this one, we're going to be looking at how to deal with two proportions in an experimental design. So again, we can use these to generalize about some larger population of interest, even if they weren't randomly selected, as long as they're randomly assigned to their two treatment groups. The other good news here is, remember that 10% rule that we always check to make sure that our sampling is less than 10% of the total population. We're not sampling in an experiment, so we don't need to check that 10% rule. Okay, so we'll do another write-up here where we will look at this idea about strokes and different medicines that might have helped. So we have two different groups that were tested, either with just aspirin alone or aspirin with another drug that I'm going to call DIPI from here on in. Okay, and which one would be more effective for patients who have already had a stroke? And here's the data on strokes and deaths during the 2 years of the study. Okay, so the first thing is to write out the standard or the study, outline the design. So here's our quick review on a design for an experiment. We want to start out with volunteers, and it's even okay to add up all of them and say that there's 3,299 people who are volunteers. They're going to get randomly assigned. And remember, the key problem here last time is we forgot to put them into groups and say how many were in the groups before we gave them treatments. So make sure that you put them into a room first before you give them medicine. Those should be two different items. So group first, then treatment. And again, I'm keeping track of numbers along the way. And then at the end, I'm saying observe or compare the proportion of strokes over 2 years. I could also be comparing the number of deaths over 2 years as well. I decided to be more positive about this and just look at strokes instead. So reading the problem, is there a significant difference in the proportion? So I know it's a proportion problem. I know it's difference. Strokes between these two treatments. Carry out an appropriate test. So I know I'm running a test to help with these answers. So again, I'm doing phantoms. This time, instead of calling them little piece of one, little piece of two, I decided to use the letters to help me. So the first one is just aspirin. The second one is aspirin plus DIPI, whatever. And the first one I'm going to write entirely out. The second one I'm just going to use those little duplicate signs, or you could use arrows down to say it's the same thing, and then I just trade out the one thing that is different. All right, so next we're going to go on to the hypothesis statement and the assumptions and conditions. So in the hypothesis, we're going to use those same two proportions and say for the null that they're equal, or if I write them as a difference, it's going to be equal to 0. And then the alternative is just going to be not equal. So I'm going to keep the subtraction in the same order and just say not equals. So then I looked for the random and I said both groups were randomly assigned to treatment groups. So that counts. For the normal, I'm going to have to check both of the groups. And what I realized was, as I was calculating this part right here, I did not know what number to put in right here. So I had to go and calculate it. So I wrote it over here. Okay, so I had to go and find those sample proportions and put them in and then check them out. Okay, so they're all more than 10, it all passes that. So next we're on to writing out the name of the test. Okay, so once again, we're going to call this a 2-sample population proportion z-test at an alpha of 0.05. I've also seen books who will write instead that it's a 2-sample population proportion difference, or difference of population proportion z-test. Either of those is fine. So next we are on to test statistic and obtain a p-value. All right, so for test statistic, they called it a z-test. We're using z's. Notice that I'm still using the sub notation A and AD. You still, again, could have identified them as 1 and 2, totally up to you. Wrote down the entire formula. Remember, this is the combined one. We always pool for proportion testing. So once I got there and I wrote it down the formula, I realized, darn it, I'm going to actually have to go and calculate it. So I took a moment and I went and I calculated. I got 11%. So 11%, 89%, 1 over 649 plus 1 over 6 over 50 is our standard deviation. We got a z-score of 2.753. So obtain our p-value. So next is to draw my normal distribution. Identify where positive 2.53 is. That's the first thing I drew on here, was just this part. Because it's a not equals, I'm also going to mirror it over here, and I'm going to color in both tails that go away or are more extreme from what we would think would be the average, which would be a 0 difference. Okay, so when I write my probability statement, I'm going to double whichever one matched the first z-score I got. So since I got a 2.753, I want to go towards the tail, that's greater than. Or you could add them up separate, and you could do one probability of z is greater than plus one probability that z is less than the negative 2.753 and add them together. In either case, we get a probability number of 0.006. So we're on to make a decision and summary statement. Make a decision is because our p-value is less than our alpha level, we reject HO. And then our summary would be, we have convincing evidence that there is, and then I go back to the top, a significant difference in the proportion of strokes between what two treatments, the treatments that are aspirin and whatever that DIPI treatment is. And I say treatment. Remember that because we didn't randomly select, we can't apply this to a bigger population. We can only apply it to this population, right? So we have convincing evidence that there's a significant difference in the proportion of these patients. So of these patients. And then because we have random assignment, we do have cause and effect. So we could say that the aspirin plus the DIPI did create better or caused better outcomes in strokes. All right, so next step is we are on to construct and interpret a 95% confidence interval of these same two, and it's going to look very much like our last one. All right, so once again, I can tell them for panic that for the parameter and for the assumptions and conditions, I can see above for the same things. The name for this one would be a two-sample population proportion Z interval at a 95% confidence interval. I have my interval formula there. This one is not using combined proportion. I'm just going to use those same ones that were listed before. So 0.125 minus 0.095. I had to go and calculate what my Z-star score was, a 1.960. Then I put each one of those in and I got a interval of 0.00867 to 0.05133. So my conclusion is, and it was right about here where I realized I made a huge mistake that I'm not going to go back and redo. We are 95% confident that the interval from, and I listed the same intervals, captures the true difference in proportion. So I went back up to the title to go and grab the sentence, and I realized it said proportion of deaths. And I just about died because there's no way I'm going to go and rewrite all of this again for death. So I just changed the words to stroke. We'll just pretend it's strokes instead. So aspirin minus aspirin plus whatever that DIPI treatment is of patients like these. Okay, so remember the idea here is it doesn't go to all population of everybody, just population of those like that were in the experiment. Cool. That is our population. That's who we're talking about. We're not talking about all people. We're just talking about people like these that took these two treatment options. All right, and that's it.